Hi everyone, thank you for joining me here virtually at SQL Bits from wherever you are in the world. My name's Paul Randall and I'm recording this here in my sound booth in Redmond, Washington. Let's get to the session, and don't forget that I'm on the chat live to answer any questions you might have. So this is Performance Mythbusters. It's one of my favourite sessions to present. Very quickly, a little bit about me. I'm a co-owner and manager of SQLskills.com with my lovely wife, Kimberly. And there's my email address, there's my blog, and my Twitter handle. I used to work for Microsoft for about 9 years. I wrote a whole bunch of the code in the storage engine, including DBCC CheckDB, and I ultimately was responsible for the whole of the storage engine. A little bit about our company. We do, obviously, training, consulting. You can get lots of online training that we've recorded at Pluralsight, and we have a bi-weekly newsletter that you might want to sign up for. So this is my life. Have a quick read. The kind of disembodied voice is Kimberly, and that's me. There's all kinds of incorrect stuff out there on the internet that I've tried to debunk over the last 20-odd years working with SQL Server. And if you want to waste an entire afternoon, go look at the comic XKCD. It's absolutely fantastic. Anyway, it's important to debunk some of these myths because myths and misconceptions persist over time, especially around SQL Server performance. And adherence to these misconceptions can lead to bad practices, people doing things incorrectly, wasting time and resources by provisioning things that don't need to be provisioned, confusion, arguments, and so on and so on. So we're going to debunk a bunch of myths. Here's how it's going to work. I'm going to put up a myth, and you have a quick think for a few seconds to think whether you think it's true or false. Now, this one obviously is untrue. Now, let's get on to the real ones. Number 1, versioning or snapshot isolation always helps performance. And of course, it's untrue. It depends what you're turning snapshot isolation on for, whether you're using true snapshot isolation or the read committed snapshot isolation. It's to help with blocking and deadlocks, okay? Or to get an unchanging view of the database. Now, if you don't need either of these things, then you shouldn't turn it on, because using snapshot isolation does have a performance hit. It creates versions. Now, a version is a pre-change copy of the record that's pushed into the version store in TempDB. Now, that means that the version store is using TempDB, so it causes TempDB reading and writing if you're actually having to use the versions. If you're not using those versions, you're adding extra workload to TempDB for no good reason. Also, when a row version is first created for a row, the row expands by 14 bytes. And so making that row longer might mean that it no longer fits on the page. If that page is in an index and the page is completely full, you're going to get a page split. So enabling snapshot isolation can actually lead to index fragmentation where you didn't have index fragmentation before. So you might get up to a 10 to 15% throughput drop for some workloads. It depends on what your workload is doing. Accelerated database recovery uses a kind of versioning mechanism as well, but it uses on-page versions where the pre-change record is actually stored on the page. And this is how the fast recovery works, because it can instantly roll back the transaction, and the transaction, it's still there on the page, but if a row needs to be read, it knows that there's a pre-change version that it should read instead by using that from the page. And again, that's a performance hit. So you're trading off whether you want to be able to recover very quickly from, say, long-running transactions for a little bit of runtime performance. The next one, the buffer manager page life expectancy counter is the best way to look at page life expectancy. In other words, pressure on the buffer pool. What do you think? Yes or no? Well, it depends. My famous catchphrase. If you have NUMA in your system, non-uniform memory access, which is very common these days, then the buffer manager PLE counter is actually what's called a harmonic mean of the page life expectancy counters from all of the buffer nodes. And that's because on a NUMA system, the buffer pool is actually split up into partitions, with each NUMA node having a portion of the buffer pool. So for instance, if you've got 4 NUMA nodes in your system, each NUMA node will have 1/4 of the buffer pool. Each of those buffer pool partitions has its own lazy writer, and it's the lazy writer that is used to calculate what's going on with page life expectancy. So if you have NUMA, then you actually have to monitor all of the buffer node page life expectancy counters rather than just the buffer manager page life expectancy counter, because it's entirely possible that you might have memory pressure on just one of the NUMA nodes and that's not affecting the other ones. And so if you're just measuring the buffer manager PLE counter, a drop in one of the NUMA nodes PLEs might not be reflected enough in the buffer manager PLE to trigger whatever kind of alerting you've got set up. So the next one, you can't override the max degree of parallelism setting. So the next one, you can't override max degree of parallelism. Well, maybe. The server scoped or database scoped max DOP setting can actually be overridden by anyone with any privilege level using a max DOP query hint. So that doesn't stop them. Now, you can track who is actually overriding your max DOP hint using extended events. So if somebody's overriding, you've got max DOP 1 set, you can use extended events to see who is actually using parallelism. And there's a blog post link there where you can actually get some code to do that. Now, if you absolutely want to enforce max DOP of 1, then the only way of doing it is by setting Resource Governor, which is an Enterprise Edition only feature, and set everybody to be in a workload group that has a max_DOP setting of 1. And that forces all connections to use max DOP 1, and that cannot be overridden. You could also, if you're not able to use Resource Governor, you could enforce max DOP 1 by changing the cost threshold for parallelism, which is the threshold at which it's going to generate a parallel plan, to be extremely high, so there's no chance that any plan is going to go parallel. The next one, availability group readable secondaries don't cause performance problems. What do you think about that? Busted. Now, here's the interesting thing. On an availability group readable secondary, no matter what isolation level you set when you're querying the readable secondary, under the covers it's converted to snapshot isolation. And that's so that the queries don't cause blocking of the replay of log records. Now that means if it's using snapshot isolation on the secondary, that means that there has to be enough space for those 14-byte versioning tags that I mentioned earlier on. They have to be there, the space has to be there on the secondary. Now the only way for that to be possible is if the 14-byte space is put there on the primary. And then a log record gets replayed and the 14 bytes of space is added to a record on the secondary. So that means that these tags have to be added to the primary. So as soon as you turn on an availability group readable secondary, any updates to that database on the primary start to add 14 bytes of space onto the end of the records. They don't actually have to be filled in with anything, but the space just has to be there, so the space is there on the secondary as well. Now, if you already have versioning turned on for that database, there's no change. But if you don't, then those 14 bytes that are added could cause rows to grow. Well, obviously the rows are going to grow, but if there's not enough space for those rows on the pages, that's going to cause page splits to happen. So that means you might have indexes on your primary where you don't have any performance issues, no page splits occurring, no fragmentation, and you turn on a readable secondary and suddenly you start getting fragmentation happening. So when you have a readable secondary, you start having to do potentially more index maintenance if you find that that fragmentation is causing a performance problem on the primary. Number 5, truncate table or partition is so fast because it's not logged. Kind of. Okay, it's actually always logged and it's fully logged, but sometimes the logging is delayed. Same thing actually happens for drop table. There's a background mechanism called deferred drop that was added back in 2000. And the reason it was done is because back in 2000, the Microsoft team started to get reports from people that the clients couldn't drop or truncate tables. They were actually running out of memory. And this understandably perturbed these people. So we investigated, because I was on the team at the time, and we found that what was going on was when a table is truncated under the old mechanism, every extent had an allocation lock taken on it, and those allocation locks were held until the end of the truncate or drop. And this was a kind of background mechanism to make sure that no other thing could use those extents while the table was in the process of being truncated or dropped. And so all that lock memory was adding up and adding up and adding up, and it reached a kind of tipping point back in 2000 where people had large enough tables that the amount of extent lock memory required to do the truncate or the drop was too much, and so the truncate or drop failed. So we added this mechanism in 2000 SP3, and what it says is, if the table being dropped or truncated has less than 128 extents, then it's done immediately. If it has more than 128 extents, then the allocation unit for the thing being dropped is kind of unhooked put onto a background task queue, and then it says done. And if you actually look in the log, you'll see that there's maybe 20 or 30 log records, and that's what makes people think, oh, it's not logged. If you then wait for, say, a minute or so and go look in the log again, you'll see thousands of log records dropping the various extents, and it's being done by a background task called the deferred drop background task. If you do begin tran, truncate table, and it says done, and then you do rollback tran, the table's still there, which proves that it is actually a logged operation. And you can actually go and look in the log as well. So, kind of. It can be very fast because it's not logged immediately, but it is absolutely a logged operation. The next one, using temporary tables for intermediate query results is always a good idea. No, it's not always a good idea. It might be a good idea for some queries, but it's not always a good idea. When you create a temporary table to hold the intermediate results, it's forcing SQL Server to interrupt the kind of flow of data through the query and persist some results on disk, which then have to get read back in again. Now, you might find that actually not using a temp table is much faster and can lead to a lower runtime. And very often what we see is that somebody at some point in a client went back and changed the query to use a temporary table and found that it became faster. And so that becomes the kind of architecture that everybody uses in that client. And so everything's done using temporary tables. Oftentimes, as I've said, we find that taking the temporary tables out can make things faster. So it's always good to compare whether to use a kind of subquery or a temporary table before you go into production, because you might find that not using the temporary table is faster. If you are going to use a temporary table, make sure that you're using them efficiently. So don't just select everything from a temporary table from a regular table into the temporary table. Make sure you're only using just the columns from the regular table that you need, and only the set of rows that you need as well. And make sure also that you're creating non-clustered indexes, if you need them on the temporary table, after you've actually populated the temporary table. There was an interesting case. One of the first clients that I actually worked on, they were having a problem where they had a system that ran once a week, and it would always blow out their TempDB and fail. And they were calculating a week's worth of information. I'm not going to go into details about what it was, a week's worth of information. But to do that, they were creating a temporary table that had 15 years worth of information in TempDB, and then just pulling out 1 week's worth of. So there's a very interesting real-world example of somebody completely misusing temporary tables. Very simple to fix that once I worked out actually what it was that was causing the problem. Myth number 7. Fully logged means you're always going to see one log record for each part of an operation. Busted. So consider if you have an index with 100,000 rows in it, and you do an index rebuild. What you'd expect would be 100,000 insert row log records, one for each record, into the new index. No, that's not the most efficient way for SQL Server to log that. SQL Server always tries to log as little as possible. What it's actually going to do for that index rebuild is it's going to create a new page in memory, it's going to fill the page up with rows from the old index, and then it's going to do one log record. It's called an LOP format page, and LOP stands for log operation. A format page log record with as many rows as can fit on that page. So it's going to log full page images rather than one log record for each insert, and that is way more efficient. So really what fully logged means is that the transaction log has enough information in it to reconstitute the effect of that transaction after a crash or restore. It's up to SQL Server to determine how much to actually log and what to log and when to log. But that's all it has to do. Myth number 8. No lock and read uncommitted means no locks. What do you think about that? Well, it's actually busted. First off, these are both the same thing. What it means is that there is a scan done on the table, and it doesn't acquire any share locks. However, there's two locks that do have to be acquired. First of all, there's always a schema stability lock, and the schema stability lock stops the structure of the table or index that's being scanned from changing, so that there's no possibility of the read uncommitted scan trying to read a page that's not a real page, for instance. Also, on heaps, it has to acquire what's called a bulk operation lock, and that prevents bulk operations happening while there's any kind of read uncommitted scan. And that's to stop the scan from reading unformatted pages, because the way that bulk operations work is they will allocate an entire extent and then allocate and use the pages as required. And to prevent the scan from seeing those unformatted pages that have been allocated but not yet filled up, we need to prevent bulk operation locks while there's that read uncommitted scan from happening. Now, there are those locks that have to be taken, but there's also latches. So just because a thread has access to a page, and it might even be locked, that doesn't give it permission to actually read the page structure that's in the buffer pool. There has to be a latch taken on the page, and this latch, it's a synchronization mechanism, ensures that if a thread is reading a page, no other thread can be changing it. So a read uncommitted scan still has to acquire share latches on those physical page images in memory to make sure that there is no possibility of reading changing data. Myth number 9, you should always plan a backup strategy. And you're sitting there thinking, well, this is a performance session, how is this possibly relevant? Well, it is, and it's busted. You should always plan a restore strategy, and I'll talk more about that in my session on backups tomorrow. You have to plan a restore strategy and then plan what backups you need to take, because if you don't, you might end up in a very, very slow restore process. Let me tell you a quick story. So back in 2004, back in the midst of time, 2004, I was out in the field on a program called Frontline, where it took senior engineers out and had them work on the front lines to learn a bit more about clients and what kind of problems clients had. And I was over in North Carolina in Charlotte, and I was helping on with product support, and I was helping on a system called the server down queue, where people call in for help, and they say, my server is down, and we help them get it back up. Anyway, this small bank called in and said, hey, we've got all this corruption. What can you do to help us? So we said, what backups do you have? And they said, we don't want to go there yet. And we're like, okay, that's kind of weird, but whatever. So we helped them take a copy of their database and restored it, and we ran CheckDB with repair allow data loss, and it deleted a whole bunch of data. And they said, no, we can't have that. And then we said, okay, what backups do you have? So this was April 2004. And they said, we have a full backup from January, and we've been taking log backups every half an hour since then. So we very quickly hit the mute button on our phones, and we kind of laughed a little bit, composed ourselves, and pressed the mute button again, and said, wow, so that's going to be a little bit of a process. And they said, yes, and they're all on tape as well. Hit the mute button, we all kind of busted a gut laughing again, composed ourselves, hit the mute button, and we helped them get it all restored. Lo and behold, they had 5,000 backups on tape. Miracle of miracles, it worked. But it took 3 days to restore. Now, a 3-day-long restore means that bank was down completely for 3 days. Nobody could take any money out, no, they couldn't have any ACHs or anything like that, and they actually went out of business because of that. They didn't plan a restore strategy. They thought they had a good backup strategy where they were in the full recovery model, they had a full backup, they were doing log backups every half an hour. They hadn't tried to do a restore. If they'd planned a restore strategy, then they'd have come up with some kind of service level agreement. We have to be able to restore in X number of hours. And then the backups that they had to take to do that would have allowed them to restore. If they'd had differential backups and more frequent full backups, they would have been able to restore within their service level agreement. Now, if your bank is down for, say, half a day, you're probably not going to change banks because it's a real pain to have to go and change everything around. But if your bank is down for 3 days, then you no longer trust them. And that's why they went out of business, because a whole bunch of people just departed from the bank. So, backup strategy is actually a performance thing. Myth number 10. The best thing to put on solid-state drives are always tempdb and transaction logs. Busted. This is something that I see out there on the internet. And so don't fall into the trap of listening to what these people say and always do something. There's very few always in SQL Server. If you've got SSDs and you can't put all of your workload onto the SSDs, you've got to investigate where your biggest I/O subsystem bottleneck is. Okay? That's the candidate for what you're going to put on those SSDs. First thing I would try to do is solve it within SQL Server. Why is SQL Server driving so many reads? Why is it making so much use of tempdb? Okay, for instance, if you can't solve it inside SQL Server, or you can't solve it enough, then that's what goes on your SSDs. Okay? Now, what about RAID level? I hear people saying SSDs are fine, so you could just use RAID 0. No, you have to have redundancy even if you're using SSDs. So you need to have 2 SSDs, okay? So that means you're using RAID 1 at least. And if you're using multiple copies of SSDs, that means it's even more important that you're putting the correct things on those SSDs. And some people say, well, what about TempDB? TempDB is temporary, so it doesn't matter if something happens with TempDB. So I can just use RAID 0 for TempDB, right? No, because what happens if TempDB gets corrupted? What does SQL Server do if TempDB is not available? It shuts down. And so that's not very available, and you're not going to get any performance at all. So even for TempDB on an SSD, you still have to use RAID and not RAID 0 to have some kind of redundancy. Myth number 11. Index fragmentation only affects range scans. What do you think? No. So this is a very, very common misconception that people think index fragmentation is just affecting range scans. If I'm not doing range scans, it's no problem. That's not true, because index fragmentation actually has 2 forms. There's the index fragmentation that slows down scans, and that's logical fragmentation. And that's because it stops efficient read-ahead from happening. And there's low page density, so in other words, wasted space on pages. And so the wasted space on pages is coming from page splits. And what a page split does is it basically does a 50-50 split. There are other cases, but let's just think about it of a 50-50 split to make room for a row to be inserted or expanded on the page. And so that's creating a bunch of wasted space on 2 pages. And it's very important to consider this, because if you've got wasted space on pages, that means you've got wasted buffer pool space. And memory is probably your most precious resource. And that's called having a lower data density. So you're going to have to do more physical reads to get those same number of rows into memory, because you've got wasted space on the pages. It also means you're wasting disk space. It also means you're wasting backup space. Okay, so that can be a performance issue, having to drive more reads and take up more memory, which stops other things being in memory. So index fragmentation isn't just about range scans. And the other thing to think about index fragmentation is, how did you get there in the first place? Because to get the index fragmentation, you've had to have had page splits occurring. And page splits themselves are a performance issue. They cause a lot of extra logging. And all that transaction log has to be backed up and restored and sent across to your mirror, scanned by replication, and so on and so on and so on. So, index fragmentation, another thing that people say is you can just ignore it. That's not true. You have to consider whether it's going to affect your workload or not. You can't just stick your head in the sand and say, oh, I've got SSDs. Index fragmentation doesn't matter. Number 12. Adding more memory is always going to help performance. No. If your workload isn't reading from or spilling to disk, then adding more memory is not going to help. Because if your workload's memory resident, more memory is not going to reduce reads, so it's not going to help performance. If your workload's not spilling to disk, then more memory is not going to help, because you're not going to need that memory to prevent a spill. So just adding more memory is not a good way of helping performance, and it's not a fix-all. There's actually some things that could be detrimental by adding more memory as well. If you've got more memory, then you've got a larger buffer pool, and so it's going to take longer to shut the instance down. So that means you're going to be losing some time from your uptime service level agreement. Power on self-test of the server, if you have it enabled, is going to take longer because you've got more memory to test. You might find that allocating buffer pool memory may take longer. There's been a bug in the past, have a look at that KB article, where it might take a long time to allocate, say, several terabytes from Windows. Warming up the buffer pool could take longer as well. What do I mean by that? When your system is running kind of steady state, there's a set of pages, I'll call it the working set. There's a working set of pages in memory, and it could be like the upper levels of various B trees, there's allocation bitmaps, stuff like that. Getting to a warmed up state of the buffer pool is going to take longer when you've got a larger amount of memory and you've got more stuff that needs to be in memory. Now, sometimes people will actually write some scripts after a server reboot, especially on a large memory system, to go out and force a whole bunch of stuff to be read into the buffer pool very quickly so that the buffer pool warms up and you get back to steady state performance. The other thing is, if you just say, well, I'm just going to throw memory at the problem, that leads to complacency. And there's going to come a point where you can't just throw hardware at the problem, and you're actually going to go and have to do some proper troubleshooting and maybe some re-architecture to help your performance. Myth number 13. Lock escalation goes from row to page to table. What do you think? No. Busted. Lock escalation does the following. It either goes from row to table, or partition if you have partition level locking, or page to table or partition. It never ever goes row to page to table. It goes from whatever granularity it is right up to the top granularity. Now, partition level locks were actually introduced in 2008 to prevent problems where lock escalation has gone to a table and the query is actually only using, say, one partition, and another query wants to do something in a separate partition. With partition level locks, those two separate queries can both be locking the entire partition that they're working in without affecting the other query. It's actually off by default, and you have to configure that per table. Number 14, Query Store does not have any performance overhead. What do you think about that? Query Store was actually put in to help with performance issues. Can that cause problems? Yes, it can. So there's actually two ways that Query Store can introduce problems. If you've got a very busy system and you've got lots of ad hoc queries, there's a thing called the query hash map. So it's a map of query hashes. Every query has a query hash. It's just a number. And entering something into the query hash map requires synchronization. And so if you've got lots of threads trying to enter stuff into the query hash map, only one of them can do that at a time. And so the other threads are going to have to wait, and you're going to see QDS statement waits. So to work around that, you could set your query capture mode to auto. That might help. You could try parameterizing your queries so that there's not multiple query hashes. And then you might actually have to disable Query Store, and that's a known issue. Now, the other thing is, Query Store persists all of its data in the database, and if there's an awful lot of Query Store data, then that all has to get loaded into memory at the database startup time, and the database will not come online until that has finished, and that could take seconds or maybe even minutes. And while that's happening, you'll see a QDS load DB wait time, and it'll be increasing. If that's an issue for you, then there's a trace flag, documented trace flag 7752, which makes the Query Store startup, when a database starts up, asynchronous. But the Query Store is going to be in read-only mode until all that data has been loaded, and then it will switch to read-write mode. So there's two ways that Query Store can actually introduce significant performance problems on your system if it's not configured properly. So myth number 15. Rebuilding indexes solves performance problems even when there's no index fragmentation. No. Well, kind of, but it's not the rebuild that's solving the problem. It's the query plan recompilation that kind of fixes the performance problem. So you could do the same thing by recompiling that query, okay? Because rebuilding an index is just going to cause plan recompilation, and that seems to magically fix the problem. And the thing is that when the query plan gets recompiled, if the previous query plan was a poor query plan, then the next one that's compiled might be better, and be better for various runs of that particular query. So again, it's not rebuilding the index that does it, it's the query plan recompilation. Myth number 16, adding an extra file to TempDB is going to help solve contention issues. What do you think? Maybe. Depends on what the contention is. Okay, so if you've got one TempDB data file and you've got a lot of contention there, and we're talking about PFS allocation bitmap contention, if you add one extra file, that may or may not help solve the contention issue. The thing is, SQL Server is going to alternate between the various files in TempDB. It's called round robin allocation. But the allocation also has to take into account a thing called proportional fill. And it's going to allocate proportionally more from files that have more free space. So if you've got one TempDB data file, and you've got all kinds of contention issues, and it's pretty full, and you add one more file, then all that's going to happen is proportional fill is going to make most of the allocations come from the new file. And so the new file becomes your new allocation hotspot, and you're not going to have any alleviation of those contention issues. So when you're adding files to TempDB to help solve allocation bitmap contention, generally add 2 or 4 more files, okay, so that the allocation system is able to make use of multiple files, and you don't have just one file being the new allocation hotspot. Number 17, database snapshots do not cause performance problems. What do you think about that one? It's busted. A database snapshot is not actually a full copy of the database. What happens when you first create the database snapshot is it runs crash recovery from the real database into the database snapshot. And then after that, any time a page is changed the first time since the database snapshot was created, it gets synchronously pushed into the snapshot. And from that point on, that page will never be pushed into the snapshot again, because the snapshot already has the preserved pre-change copy of the page. Now, there's one copy of that page in each database snapshot that exists once that page has changed since that snapshot was created. So if you've got multiple database snapshots, then every time a page changes, or I should say every time a new page is being changed, a page that hasn't changed since the snapshots were created, there's one synchronous copy per snapshot, not copy into the snapshot and then copy from there into something else. It's, say you've got 10 snapshots, there's going to be 10 synchronous copies of that page. So the more snapshots you've got, the more overhead you're going to have as well. Now at the bottom there it says, what about reverting to a snapshot? There's been I call it a documented bug, since snapshots were first introduced in SQL Server 2005, where if you revert to a snapshot, and reverting to a snapshot is a pretty cool thing because it basically just takes all the pages in the snapshot and pushes them back into the database. So it's a kind of almost instant rewind without having to do restores. But it will delete the transaction log, and it will create a new transaction log with two 1/2 megabyte VLFs in the transaction log. So after you revert to a snapshot, you're going to have to manually grow your database back, you're going to have to manually grow your transaction log back out to where it was before, so that you're not having a whole bunch of transaction log growths as your workload is going along. Number 18, online index operations do not acquire locks. What do you think about that? I actually just blogged about this a week or two ago. Busted. Now, I always might like to make this joke that in SQL Server 2005, the marketing team came up with online index operations as a term, because almost online index operations isn't a very good marketing term. So at the start of the online index operations, it has to take a share table lock. And this is to make sure that there's nobody changing the index while the version scan that online index operations use is started. So it queues up a short-term table share lock. And this table share lock, once it's held, version scan starts. It doesn't turn on versioning, but it uses versioning mechanism under the covers. And an empty index is created. It also recompiles all query plans that are touching that index, so that for the duration of the online index operation, any operation that touches the old index also touches the new index. It then downgrades the share table lock to an intent share table lock, and that's the lock that's held while the index operation is happening. At the end of the index operation, it has to take a schema modification lock, because it's going to change the structure of the table by swapping those indexes, the old one and the new one, and it's also going to recompile all queries. So both of those are blocking locks. You can kind of work around that in 2014 and onwards using the wait at low priority that says the online index operation is going to wait for either the share or schema modification lock to be granted, and after a certain number of minutes do something, either do nothing, which is kind of pointless, or stop the online index operation, or stop everybody else that's blocking the online index operation. And as a side, in 2017, there's also a new thing where you can actually pause and resume online index operations, which is pretty cool. You pause it, and the in-build index is just stopped. The version scan stops, but any changes to it are still done. You know, the kind of dual path, old index, new index operations are still done. And then you can resume the online index operation, which just picks up the version scan from where it left off and carries on building the new index. Pretty cool. Myth number 19, fill factor is used by regular DML operations, insert, update, and delete. What do you think? Busted. That wouldn't make any sense at all, because then pages would never be able to fill past the fill factor. What happens is, fill factor is a directive to the storage engine to leave space for new or expanded rows so you can avoid page splits. So for instance, if you wanted to leave 30% free space, you'd set your fill factor to 70 for that index. But it only applies during builds of indexes, rebuilds of indexes, or reorganizes of indexes. In other words, those operations will set the fill factor, and then the space is there to be used up by the regular DML operations. So you're going to be picking your fill factor, and you're going to be doing regular index maintenance to put the fill factor amount of space back again after the pages have started to fill up. Myth number 20, logging is more efficient in TempDB. This one's true. So there's no crash recovery in TempDB, which means that SQL Server doesn't have to do as much for logging in TempDB. For instance, there's no redo information in TempDB log records. So log records for changes to a table, for instance, let's say you update a value in a row, is going to have the pre-change information and the after-change information. The pre-change information allows the transaction to roll back. The after-change information allows the replay of that transaction if a crash occurs. Because there's no crash recovery in TempDB, there's no replaying of transactions, and so there's no redo information. It still has to have the undo information because, of course, you can go into TempDB, do a begin tran, change something, and say rollback. So it has to have the undo information. Because there's no crash recovery, that means there's no need to persist things in the TempDB log. So that means log blocks don't flush in TempDB when a transaction commits. Right? Checkpoints don't always flush out data pages depending on which version you're on. And checkpoints only happen in TempDB when the log becomes 70% full. The TempDB recovery model is simple and you can't change it out of that. So there's a whole bunch of things that SQL Server does to log much more efficiently when you're using TempDB. And finally, it depends. What do you think? True or false? Yes, it does depend. And I always say that the answer to all questions about SQL Server that don't have obvious yes or no answers is it depends. It starts with it depends. Now the answer isn't just it depends full stop. And don't let anybody ever say it depends as the answer to a question that you ask them about SQL Server. They have to also explain why it depends, what it's going to depend on, and when it depends. Right? So it depends gets a bad rap. People say you can't just answer with it depends, and I agree. You have to explain all these things about why it depends. Now, there is one exception. What about auto-shrink? Should auto-shrink be enabled? Yes or no? No, of course not. Auto-shrink should not be enabled. There should never be any kind of regular shrink. That's probably one of the only questions I can think of where there is an absolute yes or no answer for SQL Server. It does depend for most of the cases. Now, I added a few more things in at the end just in case I had a little bit of extra time, and I do have a little bit of extra time. So all of these things are busted, and let's pick out one or two of them. The log is zeroed when it's cleared. Clearing or truncating the log, they're both horrible misnomers because nothing actually happens apart from 0 or more VLFs are marked as no longer active. There is no zeroing out of anything, there's no clearing of anything when the log gets zeroed out. It's a very popular misconception. Instant file initialization works for transaction log files. No, it doesn't. Instant file initialization only works for data files. New portions of the log always have to be zeroed out, just in case there happens to be some data in that portion of the disk that happens to look like a SQL Server transaction log record. We wouldn't want the recovery system to try to process that when it's not actually real log data. So new portions of the log always have to be zeroed out. And what about this one? Bulk logged helps log backup performance. No, it doesn't. What bulk logged means, the bulk log recovery model, means that fewer things are logged for some bulk operations. That means that those operations are faster because they don't have to do so much logging. However, when a log backup occurs after a bulk logged or minimally logged operation, the log backup has to back up all the log that occurs, but also to make sure that the effect of that bulk operation is in the log, it has to also back up all of the data extents that were changed by the minimally logged operation. So log backup performance really isn't going to be changed at all because you've used bulk logged. Now that's about it. We're out of time. There's some resources for you, and to summarize, make sure you corroborate what you read online with a trusted source. If something sounds like it's fishy or wrong, give it a try yourself. I've blogged a lot about misconceptions, and I have a Pluralsight course all about myths and misconceptions as well. And so we're done. Many thanks for watching my session, and I hope you enjoyed it and learned from it. If you've got any questions about the content, please feel free to email me at paul@sqlskills.com. I hope you enjoy the rest of the conference, and goodbye for now.